All right, so today I'm going to show you how to work all the gas law equations, all the calculations. The calculations are found on the Star Chemistry reference material chart. It is in the section labeled Behavior of Gases. Now, the equations aren't labeled Avogadro's law, Boyle's law, Charles' law, Dalton's law. They're not labeled as such, but the equations themselves are there. So fortunately, for questions like this, you don't have to match an equation to a law. You don't have to know that P total equals P1 plus P2 plus P3. You don't have to know that's Dalton's law. You just have to know how to use the equation. So that's a good thing there. So let's get started. So we have a couple of conversion problems first that we have to know. Convert the following temperatures to K. K is Kelvin. That is just a different temperature scale. We use Kelvin in chemistry because 0 Kelvin is known as absolute zero. That is the lowest temperature possible. There is nothing below 0 Kelvin. You know that atoms, they start to move slower as the temperature gets lower. So there's going to come a point where all movement stops. Electrons stop orbiting. Atoms stop vibrating. All movement stops, and that happens at 0 Kelvin. 0 Kelvin. So to convert temperatures to Kelvin, okay, this is also on your reference material sheet. 0 degrees Celsius equals 273 kelvins. Let me write that down for you. So we have 0 degrees Celsius equals 273 Kelvin. So I have 104 degrees Celsius. So part A. So all I have to do to figure out how many Kelvin 104 degrees Celsius is simply add it to 273. Okay, and I'm going to get 377 Kelvin. Simple as that. We're just adding 273. Okay, part B, the same thing. -3 plus 273, and that gives us 270 Kelvin. Very, very simple. So number 2, convert the following temperatures to degrees Celsius. So we're going to do the exact same thing. I'm going to start over here, give myself some more room. But instead of adding 273, we're going to subtract 273. Okay, and this gives us -206 degrees Celsius. Okay, part B, 1671 Kelvin minus 273. That gives us 1398 degrees Celsius. Okay, pretty straightforward. You're either adding 273 or you're subtracting 273. Pretty straightforward. So let's look at number 3. A sample of nitrogen gas has a volume, so this is important, okay, it's telling us it has a volume of 478 centimeters cubed and a pressure why isn't it working? There you go. And a pressure of 104.1 kilopascals. What volume would the gas occupy at 88.2 kilopascals if the temperature remains constant? So we're dealing with volume and pressure. So the easy way to do this, look at your gas laws and figure out which one deals with volume and pressure. So volume and pressure, okay? Volume and pressure, that one, Boyle's law. That one's simple, volume and pressure. So what is Boyle's law? Okay, Boyle's law is P1 P1 V1 equals P2 V2. So we're taking the pressure and the volume before, that's what the ones mean before, and we're setting it equal to the pressure and volume after. The twos mean after. So we just have to figure out what is what. What are we solving for? Remember the dilution equation? We kind of did the same thing, right? Befores and afters. So a sample of nitrogen gas has a volume of 478 cubic centimeters and a pressure of 104.1 kilopascals. Those are your ones, okay? So 478 centimeters cubed is your volume. So we have 101.4 kilopascals as your initial pressure. And then we have 478 centimeters cubed for your volume, your initial volume. So we're going to divide it by P2. Divided by P2, which is 88.2 kilopascals. Okay, and working out the math, that gives us a V2. Working out the math, that gives us 564.2 centimeters cubed. 564.2 centimeters cubed. Sorry you heard my phone go off. Someone just turned in something. Let me turn my notifications off here. Give me a sec. Turning notifications off. Okay, there we go. So simple as that, right? Simple as that. We just take Boyle's law. We identify which ones are the ones, which ones are the twos. Multiply the ones together and then divide it by the third one, just like the dilution equation. Okay, it's set up the same way. Okay, number 4. We have 8.98 decameters cubed of hydrogen gas is collected at 38.8 degrees Celsius. Find the volume the gas will occupy at negative 39.9 degrees Celsius if the pressure remains constant. So what are the variables that we have here? Decameters cubed, and we have a temperature. So decameters cubed, you don't have to know what a decameter is. You should be able to recognize that if you see cubed, that means volume, okay? If you see cubed, that means volume. So we're dealing with volume and temperature. Volume and temperature, volume and temperature. What law deals with volume and temperature? Charles law. Volume and temperature. So what is Charles' law? V1 over T1. T1 equals V2 over T2. V1 over T1 equals V2 over T2. Now, it's important to know that when you're dealing with gas laws, all the temperatures have to be in Kelvin. They all have to be in Kelvin, no exceptions. So we have to put these two temperatures into Kelvin. Okay, so we have negative 39.9 degrees Celsius. We're going to add 273 to get to Kelvin. And we get 233.1 Kelvin. Then our other temperature, 38.8 degrees Celsius at 273. And we get 311.8 Kelvin. So now we have our degrees, our temperatures in Kelvin. So now we can plug everything in, okay? 8.98 decameters cubed of hydrogen gas is collected at 38.8 degrees Celsius. Those are your ones. Those are your ones. 8.98 is decameters cubed is your V1. And 38.8 degrees Celsius, which is 311.8 Kelvin, is your T1. Okay? Those are your ones. We plug those into your ones. Now, we need to rearrange this equation to find the missing variable. Find the volume the gas will occupy at negative 39.9 degrees Celsius. So find the volume. So we're looking for V2. So rearranging the equation to get V2 by itself. Okay, all we're going to do, we're going to bring T2 over to the other side. So we're going to end up with V1 times T2 divided by T1. So now we know what our 1s are. We know what our 2 is. So we just plug everything in. So let me scoot over and let's just plug everything in here. Okay, so we're going to have 8.9. You know what? Let me do that in a different color so you can kind of tell it apart from my temperature conversions there. Missed a part there. Okay, so we have 8.98 decameters cubed times our T2, okay, which was negative 39.9 degrees Celsius, but converted to Kelvin. So our T2 is 233.1 Kelvin. No degrees Kelvin, just Kelvin. And then divided by T1 in kelvins again, 311.8 Kelvin. Okay, so what does that give us? Working through that math, 6.71 decameters cubed, final answer. Now, you need to go back and check your answers to make sure it makes sense, okay? Charles' law tells us that as a temperature increases, volume increases. So the opposite holds true. If the temperature goes lower, the volume's going to decrease. So what happened to the temperature? We started at 38.8 degrees Celsius and it went down to negative 39.9 degrees Celsius. So we are expecting the volume to decrease, right? Decrease in temperature, decrease in volume. And that's exactly what happened. Our temperature started out at 8.98 decameters cubed, and the temperature decreased. So the volume decreased as well. If you had kept your temperatures in degrees Celsius, you would have gotten a negative answer. And that would not have made sense because we cannot have negative volume. So it's very important to always put your temperatures in kelvins. Let's do another one. Hang with me, let's do another one. Number 5, a sample of gas is transferred from a 75 milliliter vessel to a 500 milliliter vessel if the initial pressure of the gas is 145 atmospheres. And if the temperature is held constant, what is the pressure of the gas sample in 500 milliliter vessel? So let's figure out what gas law we're dealing with. So the problem gives us a couple of things. It gives us a couple of milliliters. I meant to do that in yellow. Let me and change to yellow. Okay, it gives us 1, 2 different volumes, and it gives us a pressure, and it's asking us what is the pressure of a gas in the 500 milliliter vessel. So pressure and volume. Milliliters are volume. pressure and volume. What is the gas law? Pressure and volume, Boyle's. So we're dealing with Boyle's law. Okay, so Boyle's law, that is P1 V1 equals P2 V2. P1 V1 equals P2 V2. Okay, so we got to figure out what we're solving for. Okay, it says, let's look back at the question. What is the pressure? So pretty explicitly we're solving for pressure. Now, are we solving for P1 or P2? Okay, are we solving for pressure before anything changed, the initial pressure, or are we solving for pressure after it changed? The sample of a gas is transferred from 75 milliliters to a 500 milliliter vessel. It gives us an initial pressure, so it's asking for pressure after the change, so we're solving for P2. Okay, so we have, let's go back over here. So rearranging the equation, all we're doing is bringing V2 to the other side. So P1 V1 divided by V2. So we just plug everything in. So we're just plugging everything in. Okay, so P1 is 145 atmospheres of pressure. Now volume 1, how do we get volume 1? Okay, it's telling us that it was transferred from a 75 milliliter vessel to a 500 milliliter vessel. So which one is our initial volume? The first one. It went from one vessel to another vessel. So from 75 milliliters, that's our V1. 75 milliliters. And then dividing it by our V2, which is 500 milliliters. Okay? So 145 times 75 divided by 500, and we get 21.75 atmospheres of pressure. Does this answer make sense? Does this answer make sense? Boyle's law tells us pressure and volume inversely related. Okay? If volume increases, pressure will decrease. If volume increases, pressure will decrease. And our volume did increase. It increased a lot. It went from 75 and it increased all the way up to 500. So we are expecting our answer to be lower than 145 atmospheres, and indeed it is. 21.75 atmospheres. Remember, if you have questions, type them in the comments, okay? And I'll answer them. We'll get back to you. So let's keep on going. Okay, so number 6, pressure conversions. We got to know how to do these too. Okay, pressure conversions. Okay, these pressure conversions, these are also on the Start Chemistry reference materials. It's under the section labeled Constants and Conversions. Okay, I'm going to write across the top exactly what it says in the Constants and Conversion sections regarding pressure. So we have 1 atmosphere is equal to 760 millimeters mercury. Okay, and that is equal to 101.3 kilopascals. You know, let me write that again. Let me start over way on the side to give myself more room. Thought I had more room on the edge of the paper there. Okay, but I did not. So let me start a little bit further down over here. 1 atmosphere is equal to 760 millimeters mercury that is equal to 101.3 kilopascals. So atmospheres of pressure, millimeters mercury, kilopascals, those are all just different units for measuring pressure. That's all it is, just different units for measuring pressure. Okay, convert a pressure of 0.0248 millimeters mercury to the equivalent pressure in pascals. So we have our temperature conversions here. Let me, pressure conversion, sorry. So we're starting off with 0.02. I'm getting ahead of myself, not a 4 there, should be 2. .48 millimeters mercury. Remember this? Remember this lovely, lovely thing here? Okay, we're doing our conversions. So we need to go to pascals. Now the closest thing we have to pascals is kilopascals. So that's where we're going to go first. So remember, if millimeters mercury is on the top in our first step, it's going to go on the bottom in the second step. And then kilopascals will go on top. So look at your conversions that I wrote down. 760 millimeters mercury is equal to 101.3 kilopascals. So that's exactly what we write down. 760 millimeters mercury is equal to 101.3 kilopascals. And the millimeters mercury cancels. Now the question isn't asking for kilopascals, it's asking for pascals. Simple, easy. What does kilo mean? What does kilo mean? Kilo means 1,000. Okay, so in 1 kilopascal, I have 1,000 pascals, right? Kilo means pascal. Kilo means 1,000. Sorry, kilo means 1,000. So we have 0.0248 times 101.3 times 1,000 divided by 760. And we get 3.31 pascals. Final answer. Simple conversion problem, okay? What I have written in red on the top of the paper, that is on your constants and conversions section in your Star Chemistry reference material. So that's there. You're going to have that handy when you take your next quiz. Okay? So we have number 7. To what temperature must 32 feet cubed of a gas at 2 degrees Celsius be heated for it to occupy 1 times 10 to the second feet cubed at the same pressure? So we have temperature, and what is that? Feet cubed, volume, temperature and volume, okay? That is Charles' law. And what is Charles' law again? V1 over T1 equals V2 over T2. Okay, V1 over T1 equals V2 over T2. Again, our temperatures have to be in Kelvin. They have to be in Kelvin. So 2 degrees Celsius plus 273 equals 275 Kelvin. So that's what we're going to use for our temperature. 275 Kelvin. That's what we're going to use for our temperature. So we have to figure out, what are we solving for? So we have 32 cubic feet. and 275 Kelvin. Okay, those are our initial volume and temperature. So we're solving for T2 because it's asking what temperature must it be heated up to. Okay, that's implying final. What do we need to get it to? What temperature does it have to be raised to? So we're looking for final temperature. Okay, so we have to just rearrange this equation to get T2 by itself. Okay, very, very simple algebra. So we have T1, V2 divided by V1. I'm not going to go through all the algebra steps. That's just first year algebra. I'll tell you very quickly. I brought T2 over to the other side, divided both sides by V1, and multiplied both sides by T1. Okay, to get everything how I want it. And now we just plug in our numbers. Okay, we just plug in our numbers. So T1, 275 Kelvin. V2, 1 times 10 to the second feet squared. I am not a fan of scientific notation. So if you want to write 100 cubic feet, fine with me. Fine with me. 100 feet cubed divided by 32 feet cubed. So it's 275 times 100 divided by 32. Now, let's look at this. Charles' law. As volume increases, volume will increase if temperature increases. Okay? So it's pretty much saying the temperature is going to be heated. Okay? The volume increased from 32 cubic feet to 100 cubic feet. To achieve that, we have to increase the temperature. So we are expecting our temperature to be higher than 275 Kelvin. We are expecting it to be higher. So doing the math, it does in fact come out higher. 859 Kelvin, final answer. Okay, so I'm gonna do one more. Thank you for sticking with me this whole time. I'm gonna do one more, and then I'm gonna leave 9 and 10 for you to practice. Okay, number 8 deals with something called the ideal gas law. That deals with everything. Okay, I like to call the ideal gas law, let me get that centered there. Okay, ideal gas law, Pivnert, very simple to remember. PV equals nRT, Pivnert. P is pressure, V is volume, N is number of moles, and R is a constant. It is on your Start Chemistry reference materials, and T is temperature. Okay, pressure, volume, number of moles, constant, and temperature. So this one, we just plug in our numbers. At what temperature will 19.4 grams of molecular oxygen, O2, exert a pressure of 1,820 millimeters mercury in a 5.2 liter cylinder? So we're solving for temperature. It's telling us at what temperature. That's what we're solving for. So we have to get T by itself. Okay? So all we're doing is bringing N and R over to the other side. And to do that, we need to divide. So PV divided by NR. That's our equation. Now, do you see the wrinkle? Do you see the little extra step the problem is making us do? Do you see it? Our equation gives us a variable for moles, number of moles, that's N. The problem gives us grams. Do you see what we need to do? We need to convert that 19.4 grams of molecular oxygen into moles. Okay, so don't forget everything you've learned in past units. You're going to need that knowledge. You're going to need those skills, okay? So 19.4 grams of O2. Okay? 1 mole is how many grams? Some of you may have this memorized by now after doing it 1,000 times. Some of you still need to look at the periodic table. That's fine, okay? 1 mole of oxygen is 16 grams. I have molecular oxygen, that's O2. So 16 times 2, 32 grams. Okay, grams of O2 cancel. So 19.4 divided by 32 is going to be 0.606 moles. 0.606. Let me double check that really quickly on my calculator. 19.4 divided by 32, 0.606. So that's our N. So now we just go to plugging numbers in. So pressure, 1820 millimeters mercury. Okay. Volume, 5.12 liters. Number of moles, 0.606 moles. And the R constant, Now, if you were to look at the STAR chemistry reference material, you would see a section. I'm going to write on the bottom of this part here, I'm going to write below it in this square what it says on the STAR chemistry reference material, okay? R as your ideal constant. It gives you 3 different values of R. 3 values of R. We have to pick the correct one. It gives us one that says 0.0821, and then the unit, liters times atmospheres over moles times Kelvin. Okay, it gives us that one. It gives us 8.31. And then the unit for that one, liters times kilopascals over moles times Kelvin. Then it gives us another one, 62.4. Then the unit for that, liters times millimeters mercury over moles times Kelvin. So we have all of these values of R to choose from. So how do we know which one to choose? The key is to look at the units. Look at the units, alrighty? Look at the units. The problem gives us units, millimeters mercury and liters. So which one of these R's has the units millimeters mercury with liters? This one. So that's the R we choose. So we're going to plug in 62.4. So let me go back to my problem over here. So we are plugging in 62.4. Let me change my color back to blue. $62.4. Okay. Now working through that math, Get rid of this just to have some room. So working through that math, I get a final answer. That's 1820 times 5.12 divided by 0.606 divided by 62.4. That gives me 246.3 Kelvin. Box that puppy up. Final answer. We went through a lot. We did a lot today, okay? I'm going to leave 9 and 10 for you to do on your own. Number 9, I'll give you a hint, ideal gas law. It's the same thing, so you're going to have to figure out what R to use. Number 10, I'll give you a hint, Dalton's law. Dalton's law, okay? So try those 2 to practice, and then I'm going to help you out more tomorrow, and we're going to have a quiz over these calculations on Monday. I'm going to help you out more on Monday. We'll do some more practice and we'll have a quiz over the gas law calculations on Tuesday. And if you stuck with me through this entire time, you are a rock star. We are chemistry rock stars. Keep doing it. Keep working. Rock stars don't quit. Okay? So go ahead and try 9 and 10 on your own. And I will say it because I haven't said it in a long time. That is it. Happy Friday.